Okay. I believe that you can hear my voice. Huh? Okay. We continue with this section. Okay. So I have given a representation for the whole diagram of the Anova. Okay. For the single factor, where just now somebody asked me that the why double dot we call as a grand mean, or we also can calculate using the following formula. Just total out all the observation divided by an. Okay. So this one is what you have here. Then we compare the means of the each one right here. Okay. So let us see after you know about this diagram, this table, then we will see how are we going to analyze it. Okay. So the idea of the analysis of variance is actually partition the total variability into the different components. Okay, so means that the total variability is like the total variation in the response into the component that are consistent with the model for the experiment. Okay, so what is means by the total out the variability? So you can see from the model here. May I know whether you can hear my voice or not?
Yes.
Okay, thank you. Yeah. So if you can recall back just now what you have the observation, we have Yij is your observation, or we call as a response variable. So the response variable will affected by the overall mean. This one, the tau is a stand for the overall mean. At the same time, they also were affected by the second one will be the tau I. What is a tau I? It means that the treatment effect means that you have a level 1, level 2, level 3, and so on. So the first level is called the treatment for the I level, the first level effect. So the observation will depend, they were affected by the overall mean and the treatment effect, and of course is a random error here. They have errors, where this error is called the experimental error, is normally identical distributed with mean 0 and variance sigma square. Okay, so your observation will be affected by the whole thing here. Okay, so what we can see from the here, if your mean, everyone have a constant overall mean. If the tau I, it means that the treatment effect. If all the observation have a same treatment effect, so means that the mean plus the tau will be have a. So if your treatment effect will be the same, so it means that all the levels you have a same effect, means that it's no difference in the all the level. Okay, so the model was given by the following one. So there are several ways to write the model. Okay, so just now you can see that the model here is a Yij is equal to mean plus a tau I plus a epsilon I is called the effect model. Why it called effect? Because you see that this thing is an effect. Okay, tau I is a tau, if your I is from 1 under A, so you have the tau 1, tau 2, tau 3 under her. So you have a different effect of the model. Or if we can group these two together, become the single one. So this one is become the mean I. So this one is called the mean models. So I introduce to you this one is because sometimes the representation of the formula, the what different textbook, they use a different name. Okay. So then in the following way, then you can use a regression model can be used to do the analysis. Okay, so actually this thing is just one of the linear model. Linear model in the sense that you have a Yij, you have a mean, you have tau, you have an error term. Okay. So now we start going to do the analysis of using the analysis of variance. So just now I have mentioned to you, we are studying of the total variability is try to partition it out. So how are we going to partition it out? first thing we need to know how they arrange it. So the total variability can be measured as a sum of the total sum of square. So the notation is given by the SST. T here is stand for the total, or sometimes you can see it, they use a SS for the total. Okay, the total variability is a measure by the sum of the total variability. This one you can see that the sum out all the observation minus the overall mean square. If you can recall what is the formula for variance. If you have a one single sample variance, then you have a S square is your variance. It's an unbiased sample variance will be n minus 1. Then you have a summation of the xi minus the x bar square. Means that you use all the observation minus the mean the square. So this one is called the variance of what you have. So this formula is same like the total sum of square. So means that use the observation minus the total mean square. So this one we call as a SST, or sometimes you can see they use the SS total. Okay, SS total is stand for sum of square. So how the analysis of variance is do it? They will try to partition it for this component. Okay, this component we can break it to the following one. We still have this thing. Okay, I just rewrite it this part. We have a okay, I just write in the following form and then plus the okay. So if you observe here, here is observation minus the overall mean square. Just now I have mentioned to you y bar dot dot is stand for overall mean. Observation minus the overall mean, then you sum it out. They can written as a following one. As you can see out, I put the additional term of here, additional term of here. These two you can cancel off. Yij minus the y double bar is still the same thing. Okay. So you can be written as this part, where we try to break it to the different component. So if you expand the bracket of here, then you should be get the double summation. Of course, you have a first one. The first term should be this one. I will directly will put it yi dot minus okay, the first term will be square. Okay, the second term also is a square. Of course, this one, the bracket is not necessary. Okay, the first term. Okay, the first term square, the second term square, and then plus the 2 times of the summation. Okay, so you will divide it into the 3 component here. Okay, you divided into the first component and then divided into the second component plus the third component. But if you observe that these 3 components, this component, you will get the answer is equal to 0. The cross product will equal to 0. The reason is because if you can see that this summation is there's just a I and j. I just put the I and j here. Okay, this summation of the j here, the I here is this one is only depend on I. So therefore, this one can bring it out from the summation. Okay, maybe I will show you this one. So you just now you have this term is 2 times the summation Okay, so this summation is they depends on the because this summation is depends on the I and j. So because this one is does not have a j here, so you can bring it out become this form. So this one is summation. If you observe this summation, so this summation will to the 0 because it's summation of the j. This part you have a summation of the j here, but this part you do not have a summation j. So we just concentrate on this part here. You have a 2 times the summation of the I. Okay, so if this one, your summation of the j here, if you summation of this one, then you get your, okay, you summation, you get the yi dot. Okay, because you sum it out for along all the j, then you get the yi dot. Minus away, you sum it a j, then you get the you summation of the j here, then you will get your the value here. Okay. You repeat it for the j times. The j is starting from the 1 until the end here. Okay, so if you repeat this thing for the n here, then you get the n times the y bar I. So if the n times y bar I is actually is n times the y I dot divided by n. Okay, so from here we will know that so this one is a y bar I divided by n. So because you summation of the n, they have a n here. So you cancel off, these two will cancel off. So therefore, the whole term will equal to 0. So this one will be explained to you. The term of the cross product will equal to 0. Okay, so the cross product of this part will equal to 0. So means that your summation of the here, I can rewrite out your summation of the sum of square. What I can say that is a sum of square for the observation yi minus a y. They can be written as a 2 component here. Of course, here is a I and a j. I will write the complete one. This one, we can be written it as the n times the summation of the okay. So this one is the total variation. They can be partitioned into this part and they partition into this part. Okay, so this one we call as a SS for the total. I use a notation as SST. This one we call as a sum of square for This one we call as a sum or square for the error. Or you use a notation as SSE. Okay, so how you want to recognize that this one is sum or square for treatment, this one is sum or error. So if you observe the formula here, this one is a mean for each level minus the overall mean. This one is an observation minus a mean from each of the level. If you recall back what is the diagram here, then you can see here the diagram of the table. Okay, so you can see here, if you use the observation minus the mean here, then you can get the variation within the mean here. You get the variation from each of the level. If you use the mean here minus the overall mean, then you can see that the variation of the different treatment level. Okay, so this one is what they do it. They have an overall mean as a benchmark. They use the observation minus the mean here, means that they get the sum or square for total. If they want to get the sum or square for treatment, they use the mean from the first level minus away the mean of the overall mean square. The second one, they minus away square and so on. Okay, so they want to find out the variation, this mean with the grand mean, and the variation of the inside the observation for each level with the overall mean, inside the observation here with the overall with the mean here, and then square it out. Okay, so they want to compare the two components of variance. Okay, so from here, what we can observe from here, you can see that the sum or square for total can be break to these two components. Okay, this one you can see from this page, the page of here. SST is equal to S treatment plus the SSE. So the treatment means that you use the mean for each level minus the overall mean. So what you can observe from this formula, what we want to say that a larger value of sum or square for treatment reflects that the last difference in the treatment mean. Okay, if you have because this formula is the treatment mean minus the overall. So if you have a last variation here, means that we know that there is a last difference in the treatment mean. So this one means that the treatment means have a different performance. Okay, or the mean is not equal. The second one, a small value of the sum or square for treatment likely indicate that no differences in the treatment mean. So the small value will indicate no differences here. Okay, so the former statistical hypothesis, I always will say that is a H0 is a mean 1 equal to mean 2 until equal to the mean A, because we want to compare the A level of the population means. The H1 is actually testing is at least one pair. We do not know which pair is it, but we know that if at least one pair of the mean is different, then we will reject the H0. Okay. So now after you know, you can partition it into the different components of them. Then of course we need to know what is a suitable statistical the test to be used. Okay. Then before you know the what is a statistical test to be used, then you need to know some other things. The sum or square cannot be directly compared to test the hypothesis of the equality means, because the sum or square, we do not know what is the distribution for the sum or square. So we cannot directly test it, because the value just now I say that the small value, the large value does not mean anything. So we need to have what they call as a mean square. Just now we have a sum or square, now you get the mean. So how to compute the mean square? You need to know the degree of freedom. A mean square is a sum or square divided by its degree of freedom. So the degree of freedom under the total sum or square is equal to an minus 1. This one is always a fixed one, is an an minus 1. The degree of freedom for the treatment will be how many levels you have? You have a A minus 1 level. So the degree of freedom for treatment will be A minus 1. The remaining one is a degree of freedom for error will be the AN minus A times N minus 1. So this one is the last one. Okay, for the first one, this one is a total will be here. So you study all the ANOVA, your degree of freedom for total will be always fixed as the total observation minus by 1. Okay, but your degree of freedom for the treatment will be keep changing, depends on what kind of design you are referring to. So for this case is a single factor with the A levels, so the degree of freedom for treatment will equal to A minus 1. Okay, the degree of freedom of error will be AN minus 1. You can see that the left hand side and the right hand side, the total will be the equal degree of freedom. Okay, so once we know the degree of freedom, if you use a sum of square just now, you divide it by degree of freedom, you will get your mean square. So MS is referred to the mean square. So this one is a mean square for treatment. This one is a mean square for the error. Okay, so now if you have a mean square, then we can compare it with the using the ANOVA table. Okay, so finally you need to calculate out the mean square. So if the treatment means are equal, the treatment and the error mean square will be theoretically equal. Means that these two values will be theoretically equal. If the treatment mean is differ, then the treatment mean square will be larger than the error mean square. Okay, so if the treatment will be, there is a difference, so they should be, we expect that the mean square for treatment will be larger than the here. But how large is it is considered as a differ, then we need to have some benchmark. So we need to know what is a suitable distribution for it. Okay. So this one is an ANOVA table. Finally, you will go to the ANOVA table. Okay. So the idea of them is break it to the different component of the variability. So this one is called the sum of square. Just now I have introduced for you. This is a formula for sum of square. This is a formula for sum of square for total. So because we know that the sum of square for total will equal the sum of square for treatment plus the sum of square error. So we no need to know the formula for calculating the sum of square for error. Once we know the total and the treatment, then we use the total minus the treatment, you get the sum of square for error. Okay, and then these are the corresponding degree of freedoms. So once the sum of square divided by degree of freedom, you will get your mean square, and the second one will be mean square. So the final one, if we get the mean square, okay, this thing you need to refer to the statistic, what you maybe you will learn it, testing the variance of them. Okay, if you have a mean square divided by another mean square, they will F distribution. Okay, so this F is stand for the F distribution. Okay, the reference for the F is equal to the F distribution. So the F distribution will behave like the here. The shape of the F distribution will behave like this one. Okay, they will keep changing according to the here shape. When in the F distribution, they depends on the degree of freedom and the degree of freedom too. If you want to looking for the F distribution, you need to refer to the 2 degree of freedom. The first degree of freedom will be the A minus 1. How we want to know the first degree of freedom? You refer the here. So this one, MS treatment, the degree of freedom A minus 1. Therefore, the first degree of freedom A minus 1. The bottom here, MSE, the degree of freedom N minus 1. Therefore, it's a N minus 1. N minus 1 also equal to AN minus 1. Okay, so this one is how is it? Why we want to from the here go to the here. For students who are don't know why they come from the F distribution, then you need to recall back. Maybe you need to study more about how the F distribution come from. Okay, the F distribution will come from the F distribution will come from the 2 chi-square distribution. I put the chi-square distribution 1 divided by degree of freedom 1 over chi-square distribution 2 divided by degree of freedom 2. Okay, this one, if you want to get the F distribution, you need to get from the chi-square distribution. So if the chi-square by their degree of freedom, the second chi-square distribution over degree of freedom, then you get the F distribution. So where is the chi-square? Actually, this thing will follow the chi-square distribution with their degree of freedom A minus 1. This the SSE is another chi-square distribution divided by n minus b. Therefore, you use this one over this one, because this one over this one is to get the first part. This one over this one, you get the second part. Then they form the F distribution. So this one is a reason why you need the mean square. Okay. So they refer to the F table. So the F distribution, they depends on the 2 degree of freedom. Okay. So the reference distribution will be the F distribution. So once you get your F naught, then we compare with the theoretical or the critical value. If they fall in the rejection region, then we reject the H naught. Otherwise, we do not reject H naught. Okay, so we reject the H naught if we reject the H naught. We reject a H naught if the F naught is greater than the F value from the table. Okay, so this one is meaning that if let's say this one is meaning that you calculated out the F naught. This one I will put the F distribution like this one. So you need to assign the certain percentage of the type 1 error, the probability of the type 1 error. Okay, when you're testing the hypothesis, you need to assign the certain alpha. Alpha is referred to the type 1 error just now I have mentioned. Okay, you allow for the 5% error or the 1% error and so on. So this one, based on this one, you will get your value from the F table. Okay, the F value from the F table. So this F value will refer to the here, this value. Okay, then once you get this thing, then you based on the data, you can calculate the F naught. So the F naught is either fall at the here, this stage, or they fall at here. If they fall at here, then if they fall the F naught at here, then you will say that is do not reject. Okay, if the F naught is fall at this stage, is do not reject. Otherwise, you reject H naught. Therefore, you can see that I will say that reject the H naught if the F naught is greater than the F alpha here. Okay, if the F naught is fall at here, then you reject the null hypothesis. Okay, this one is what we do it manually. But with the statistical software, you can get another approach is called the p-value approach. Once you get your p-value, then you can directly compare with the alpha, whether you reject or do not reject the H naught. Okay, so this one is from the beginning until now. I will tell you how to formulate the Anova table with how is it the analytic variant is working. Okay, so the idea is try to break the sum or square to the different component. So if you understand about this thing, the following like the factorial analysis, also the same idea. They try to break it to the different sum or square component. Then with their corresponding degree of freedom, and then you test it for the F test. Okay, so if we study a single factor, 2 factors, 3 factors, and so on, so this one will increase only. You have a different component become more and more, but the idea will be similar. Okay, so this one is a sum of square. Okay, so to calculate the formula, if you want to do it manually, to calculate this one, the sum of square for total, you need to do it, you need to supply the mean for each of the levels minus the overall mean square. Then you do the summation. Similarly, for the sum of square for total, you need to use the observation minus the overall mean square. Then you total out all. So if you do in this way, then you get your sum of square for total, sum of square for treatment. Then you get the sum of square for error. You no need to do the calculation again using the formula. Okay. So if you refer to here, if you refer to the calculation parts, to simplify your calculation, what we can do is a sum or square total, is even by here. But if you expand the brackets, then you can make it as simple as here. So this one means that every observation square it out. Okay, every observation square it out. This one means that the total, you total out all the observation, you square divided by n. Then you already can get your sum or square for total. Instead of you do it step by step, you sum it out for the observation minus the overall mean square. Okay. Similar, sum or square for treatment is supposed given by this formula, but if you expand the bracket, you can simplify as the following one: is sum or square for yi square divided by n minus the overall mean square divided by n. So you can observe that this term, and this term, they are the same. Okay, so in that case, you can be simplified your calculation. Okay, so this one is where you need to do it, need to understand about the idea of the sum or square. Okay, then you will get all the sum or square here. So let us go through the following examples. So this example is the same like this just now, the RF power. Okay, we want to test for these 4 levels. We have 4 levels here. With each one is 5 replicates. Then just now we have all the overall total. So if you do the analysis, you perform the same that just now the manual formula, then you get your sum or square. This is output from the software. Okay. So this one is an output here. They will tell you, okay, this one is what is a sum or square. This one error, what is a sum or square. What is a total sum or square. Okay, instead of using manually, then you can be calculate here with their corresponding degree of freedom. Because this degree of freedom, we can guess. RF power, we consider 4 level. So definitely a degree of freedom is A minus 1. Definitely must be A minus 1. You have a 4 minus 1. So this one we can get, we can know. This one also the sum or square for total, the degree of freedom always must be n minus 1. So this one you don't know, do not have a wrong, because you have a 5 times 4, you 20. 20 minus 1 is 19. So this one we will know is 3. So this one also have a formula. We no need to go to memorize it. You use a 19 minus 3, you get 16. Okay, so you will get your until the F0. If you do it manually, you'll get. So if you are using the statistical software, they will give you additional part of here is called the p-value. The p-value here will be less than 0.01. So how we want to make the decision part will based on the p-value approach. Okay, so just now you still remember we have a H0, mean 1 equal to mean 2 equal to mean 3 equal to mean 4. We are testing the 4 means. These 4 means whether equal or unequal. Okay, so we want to know that whether the H0 or H1. H1 just now I say that at least 1 pair of mean is different. Okay, at least 1 pair of them is different. This one is your hypothesis you are going to test. So how I want to make use of this one to compare, or I can use this one to compare also. If I want to refer to this one, then I need to refer to the F table to get what is the value for the border point. Okay, so if I want to use another approach, then I need to have this one. I will use a p-value with the alpha. If the p-value is greater than alpha, then you imply that you do not reject H0. Okay. Another thing is if you refer to the p-value less than alpha, then you imply that you reject H0. So in this scenario here, I do not give you the alpha. Alpha is just the error. Because you carry out any hypothesis testing, you need the error. So if let's say the alpha, we set it as 5%. Okay, we allow for the error of the 5% when we carry out the hypothesis testing. So as you observe here, in the Anova table, they already calculate for you the p-value. The value is less than 0.01. If we compare with the alpha here, we can see that the alpha will be larger than the p-value here. So if the alpha is larger than p-value, we directly will know the conclusion of this analysis. We will have a reject the H0. Reject the H0, it means that the mean is not equal. Means that at least one pair of the mean is different. Okay, so this one is how we want to make the conclusion based on the Anova table. So for those of you who don't have the knowledge on the statistic, this p-value greater than alpha, p-value less than alpha, this is one of the approach to carry out the hypothesis testing. Okay, you can be recall back your previously what you have done. You can be based on this f value, but I do not have a table with me about this value, therefore I don't see it. Okay, maybe I can let you see the f table. The f table what we have here. The f table is here. If you can see here. Okay, so if I want to find out, if I want to using the here to make the decision, also I can do that. Just now in my previous slide, I say that you compare here. Okay, so now if I want to compare, I have two comparison. One of them is based on the p-value here. Okay, if we set the alpha here. So if I want to use the f value here, then means that for the alpha 0.05, 0.05, then I need to look for the what is the value from the F distribution table. So just now I have shown it to you. This one is a 10% alpha with 10%. We just want the 5%. Okay, this one is a 5% alpha. So the first degree of freedom, we need to refer back what you have here. The degree of freedom for the first one is a 3. The second degree of freedom is a 16. How do I know the first one is 3 and 16? Because how do you get this value? This value, you use the first mean square divided by second mean square. So the degree of freedom is 3 and 16. So if we refer to here, I will refer to alpha 0.05 with the value of 3 here, the 3 here, and the degree of freedom 16. If possible, I get it. Okay, it's a 3.2389. If I do it manually, so I refer to the table 3 and 16 is 3.2389. Okay, so this is a critical point. So as you can see from here, your 66, okay, the 66, the value 66, all in this region here. Okay, they will fall at here. The value 66 here will fall at this part. Okay, they fall at here. It means that you have to reject the null hypothesis. Okay, so you can see that once you set your alpha, every test you need to set your alpha, then you will know whether you reject or not reject. If you base on this value, then you need to compare with the value from the table. But when you start working, of course, you don't bring together all the table. So therefore, we base on the p-value here. So we compare this probability with the alpha. Alpha also is a probability. Then if you compare it, you can observe that. You can observe it. If you can observe it, the alpha is larger than the p-value. So this one is what you have. You still reject H0. So you using any approach, also you'll get the answer reject the H0. Okay, so this one is what you can do for the analysis of variance. So here actually I show you something about all the codes here is actually get from the R. okay, from the R, but I do not require you to use the R to do the computation. If you have any of the statistical software, you want to produce a result, also you can do that. But I just supply here for you the code only if you want to calculate for the see the mean and standard deviation for each level. Okay, of course you can use any of statistical software to do that. To perform it, first thing you need to read your data first. You need to read your data from the to the R. After that, you can be get the summary of here. Okay, myself is not very. All the codes here is you can be go to the internet to search it out. Okay, so it's clearly we know that we are doing the grouping of them according to the RF power. Then after that, you present the sample size, the mean for the each rate, and the standard deviation for each rate. So this one is a mean for the each one. Okay, so the mean you can see from here. The mean already show you here 551, 587, 625, 707. Okay, so this is a mean. Of course, each one also can be see the standard deviation. Okay. Just now, this one is a refer to the table you have. Okay. If this one is a refer to the they are using the F0.1 alpha or the 5%. Okay, depends on what is the percentage you use, but your F value will fall in here, or you reject the null hypothesis. Okay. As I mentioned, calculation of the Anova table can be used using the computer software. Normally, I will use this software is a Minitab, but unfortunately, this software is not available anymore here. And then, of course, you can use the SPSS or R. But for those students who are willing to get the Minitab, you go to the Minitab website, they can register monthly software. Because this type of the software is like the Excel format. So you no need to do any programming. So you just put in your data. After that, you click, they will come out the output. Okay? Instead of the R, you need to do the programming. But even though in the R, you also have a certain codes here. So here, I show you the R codes here. For this course, it's not necessary you need to learn the codes here. So this one is I just reading the data. I already key in the data. I just do the reading of the data. Okay. What the data I have key in is I have key in the data according to here. I just key in the data in the Excel according to the here RF power and the each rate. Okay, I key in two column. Of course, the run order is after I run the randomization, then I have to get the third column. I save this data file as a CSV format instead of the Excel format. I save it in the CSV format. Okay. I just run the one-way Anova. This one is a one-way. The name. I just use a one-way Anova. The Y. This one is your Y. This one is your treatment. Your data set is come from where? Okay. Then they already produce for you the Anova table. The RF power, you can compare all this value with your just now doing the manual calculation, they are the same. Okay, so you will know that based on the p-value here is so small, then you reject the null hypothesis. Okay, so you reject the null hypothesis in this case. Okay, so this one is hello, yeah.
Doctor, yeah, we doesn't have the output on our notes from the spectrum.
Yeah, yes. So therefore, I show you this one, but this slide you can take it. I will share this slide in your spectrum later on.
Okay.
So it's useful for you. Why I don't put it? Because later on I want to writing something here. Yeah. So this slide I will give it to you one. You don't worry.
Okay. Sure.
Okay. Yeah. Okay. So this one is all this code is R codes. You can go to the help in the Google, search the code out. Okay. So this is an Anova table in form, similar to what you have previously. Similar to what you have here, you can see 66.8. So similar to here is a 66.8. Okay, 66.8 here. Okay. And then once you once you have your answer, once you have your answer, you know the answer is a reject the H0. So you know that the mean will be different. Okay. So after that, because you still remember at the first few pages, I have mentioned to you that everything we done, we need to check the assumption. So what is meaning by checking? Because in checking the assumption, we need to go back to the model. Okay, model adequacy checking in the Anova. You still remember if you have a Yij will equal to the mean plus a tall I plus the excellent Ij. This one is a model we have. Okay, it's a model. It's a model of the one-way Anova. Okay, the model here. So this model also, this is an error term. This is an error term, but this error term, we have a certain, we will assume that they follow the normal distribution with zero mean and variance sigma square. Okay, this one is an error term we are here. So we assume the model we have is this thing. So of course, when we run our analysis, this is a true error. We do not know. Therefore, we need to calculate the error from the sample. Okay, so the error for the sample is called what they call as a residue. So I will show you in the next slide. So the error from the sample we call as a residue, and then we can use a residue to check the assumption. Because you have assumed before that your error will follow the normal with zero mean and the sigma square. So therefore, we need to check back the assumption of the model. Whatever you fit, you need to check whether they fulfill the assumption. If you do not fulfill assumption, they say the assumption is violation. So means that you assume at the beginning is wrong. So this one is implied that whatever you have the analysis previously from here, this one can run the result, but your analysis of the model you assume is wrong. So the result may not be accurate. Okay, so this one is a three assumption we need to check from the model. Okay, so how our assumption is always will have it, because you can see that we say that it follow normal. That's why we check the normality. There is a sigma square. There is a constant variant. Therefore, we check the constant variant. Observation obtained must be independent. Therefore, we check the independent. So these are the three assumptions we need to check. Okay. So how are we going to check? We cannot use the excellent here because this is an error term, is a true error. So therefore, we need to check using the residue. So what is meaning by residue? Residue is get the, you have a observation, your residue will get from the, you have an observation. Okay, I use a notation as a here. Residue, we'll use the notation as a Eij. Okay, E is stand for the residue here, will be equal to the observation minus the fitted equation. Okay, so this one is called the residue. Okay, I can be, okay, so the residue is give the notation Eij is equal to the Y minus the fitted equation. Then this thing is called the residue. Okay. Know how to calculate the fitted equation. Yij minus the fitted equation in this case. Okay, so what is the fitted equation in this case? You can see your model. Your model will be given by here. If you want to refer to the model, you want to refer to the fitted equation, then the fitted equation will be the y hat ij will be equal to the mu hat plus the tau I hat. This one is called the fitted equation. Okay, once you get the fitted equation, it will be given by the here, then the error of course is no more. Okay, So the filter equation, I can replace it as the mu hat minus away the, plus the tau I hat here. So the filter equation for the for our one-way Anova will be given by here. So Yij, okay, minus away. This mean is referred to the overall mean. So how are you going to estimate the overall mean? You can be estimate the overall mean using the Y double dot. Because just now you can calculate the overall mean from the sample. Therefore, the good estimate for the overall mean will be here. So how are you going to estimate your tau effect here? So to estimate the tau effect here will be given by the mean for the each one minus the overall mean. Okay. So how I get this thing, you can be referred to the textbook. You can refer to the textbook here. Okay. So you have this thing. So finally, you can get it. The residue of this case will be equal to the Yij minus away. These two cancel off. You get the mean for the I dot. So to get the residue under this model is given by the Yij minus the Yi dot bar. Then you can get your residue out. Okay. So the residue, we can do the computation one by one. Okay. So in this table, in fact, you can see that just now you get the answer is a 575. I just show you how this table is. Okay. So just now I have mentioned to you, residue will be equal to Yij minus their mean. So this 575 is the data is 575 is the data itself. So to get the residue for the first cell I refer to here, maybe I draw the line here. To get the residue E11, the first cell of here. So how we want to get the residue? We just use a Y11 minus the Y bar 1 dot. Okay, Y11, the observation for the first one, it should be the 575. As you can see from here, is 575. Minus the Y bar 1 dot. The mean for the first row is a 551.2. So you will get your residue out. 575 minus, you get is a 23.8. So it's given by this one. Okay, so the second cell is a Y12. I use a notation, so it's 112 minus a Y1 dot. So I have a 542 minus away the 551.2. So you get the answer is negative 9.2. So this one is a 1. Okay, so we want to get is all the residue out. If you do it manually, you will get all the residue out. Okay, okay, so this one is I explained to you how to get the residue. Because different models have a different formula to compute their residue. For this one way Anova, this one is a way. But once you know what is the definition for residue, later on the rest of them is the same, except the Y-hat model will be different. Okay. So the first one is checking for the normality assumption. The first one is checking for the normality. Normality assumption. Okay, so for the checking of the normality assumption, if you recall back, what is the assumption of the here? We assume that this epsilon is follow the normal with zero mean and sigma squared. So we need to check whether they follow the normal or not. So one way to do it is using the normal probability plot. So the line is here, the line is appear here. So if the point is fall on the line, can be checked. We can say that they follow the normal distribution. If they deviate very much, then it's not the normal distribution. But of course, from the graphical here, it's very hard for us to see clearly Then instead of using the normal probability plot, of course, we can use a histogram. We can carry out the goodness of fit to check whether this assumption is fulfilled or not. Okay, this one is the first one, the first plot. So if you want to check the second one, will be the constant variant. If you want to check whether the variance is constant or not, then you check the you plot the graph for the residue. Residue is Eij versus the fitted value. Fitted value is a y hat ij. Just now the y hat ij is equal to y bar I dot. Okay, the fitted value. Okay, so if you versus this one, if the point is you can see the length of the point for all the thing, they are almost the same length. So therefore, the constant variance will fulfill. So this one is the second plot. You put the residue versus the fitted. Okay. For the first one, you can check in for the normal probability plot. Of course, beside the normal probability plot, you also can carry out the goodness test. Okay. Or you also can be plot the histogram. Okay, to checking the data follow the normal distribution or not, the former test will be the goodness of fit, or you can be draw the graph of this thing. Okay, so the second one is checking the constant variant. You need to plot the graph is a residue versus a fitted. So if the residue here versus a fitted, if their length is almost the same, then we say that they have a constant variant. Okay, and then to the third one, you check for the independent. Okay, so is it they are independent or not? If they do not have any obvious pattern, then it's considered as independent. Over here, you can see the point is fluctuate. Of course, they do not have any obvious pattern, then it's a independent. So if you want to plot this plot, then you will plot the residue versus the run order. What is a run order here? Is just now I mentioned for which one will run first. Okay, so here is the observation number 13. Okay, the run order is number 13, number 14, number 8, 5. This one is the order. Okay, so you plot your residue versus the order. So the order for the first one is the residue for the first one is 3.6. The second one is 18. So you can see from here this plot. The first one is 3. The second one is roughly around 18. Oh, then you plot this one. If they do not have any obvious pattern, okay. So all these plot I'm using the R to produce the plot. Okay, but if you are using the Minitab, if you have a Minitab, you go register for the free Minitab, then Minitab directly will show you all the 4 plots together. The first plot is normal probability plot. The second one will be the histogram. The third one will be the residue versus a fitted. The fourth one will be residue versus a run order. So if they do not have any pattern, then it's independent. If the line is almost the same length, then it's considered a constant variant. If they fall on the straight line, then we can say that it's a follow the normal distribution. Or you can see the shape of here, even though it's not the perfect, but they still have the tail is down, then we can say that they follow the normal distribution. Okay, so this one is checking the assumption. If the assumption is correct. Okay, so this one is what I want to discuss until the page number 31. We still have some more to go. Okay, so I think that's all for the today. Any of you have a question? Okay, for those of the students who are don't have any background on this course, so you maybe need to recall back or never mind. You just take out the textbook, then you just read it out. Okay. Okay, if you're not sure anything, you just contact me. Huh? Yeah. So for this slide, I will put it as a solution 1 because I stop until where I will put it. Then I upload to the spectrum so that you can copy. Continue with here. Then I will upload the updated here. Then you use it for the latest one with the complete set of the solution. Okay, and then with my explanation. Any of you have question?